everyone. Hello. Do you hear me?
I'm able to hear you.
Okay. Just 1 second. I will try to adjust my screen. And yeah. Okay. I will start in French after that. I will switch in English. Bonjour tout le monde, bienvenue dans notre session Archive Friday. And hello everyone, and welcome to a new Archive Friday session. My name is Rodrigue, and I will be your host today. Seme is not here today. Archive Friday, as you know, is a weekly online event that takes place every Friday, of course. Our goal is to bring together experts and technology professionals, share practical experience, and also discuss topics related to architecture, cloud data, artificial intelligence, of course, and also a business application. Today, we are very happy to welcome Sujay. His session is the safety share architecture reliable AI agent for high-tech production environments. As you know, AI agent can fail differently from traditional application. Sometimes they continue to produce confident answer even when the quality of those answers is, I can say, decreasing. During this session, Sujay will explain how the safety layer can be placed around to enforce important rules and production system. And so this session is based on a real world experience in health environments. You can post at every Friday your question in the chat, and I will answer them during the presentation, no, at the end of the presentation. And Sujay, thank you for being today. Could you please introduce yourself before starting your presentation? The floor is yours.
Amazing. Thank you so much for that great introduction, Rodrigue. So, hi everyone. Thanks Archie Fridays community for having me here today. I'm Sujay. I'm a software development engineer at one of the world's largest e-commerce and cloud technology companies. I'll and a lot of my recent work has actually involved building large scale healthcare software systems. So I just wanted to kind of share a disclaimer that the views that I'm sharing today are my own, and the material comes from the combination of published research, production, case studies, and the architectural patterns I've been studying, basically. So what I want to talk about is the point where AI stops being a demo and starts being a part of a real production system. In a demo, a strange answer is interesting. Maybe it becomes a screenshot or a funny Slack message, but in pretty important systems like healthcare, finance, industrial control, or compliance, that same funny answer can become an incorrect prescription, a financial decision or a dangerous machine action, or potentially something that can be illegal. Um, right. So the question is not simply how do we make the model more accurate. The question is how do we design a system so that a probabilistic component cannot create an unacceptable outcome. So the pattern I'll use to answer that is what I would call a safety shell, and that's the topic for today. Yeah. Okay. So let me start with like a real example. So there's something called sepsis. What is so? Sepsis is the body's extreme response to an infection. A human body's extreme response to an infection. It can progress very quickly. So detecting it early is pretty important and can actually save somebody's life. So there was this AI model called the Epic Sepsis model. It was integrated into electronic healthcare systems used by hundreds of hospitals in the United States. The idea was pretty straightforward. Continuously evaluate patient data and alert clinicians when the patient appears to be developing sepsis. And on paper, it looked pretty promising. But an external evaluation of the University of Michigan actually found a hospitalization level area under curve, AAU ROC, of about 0.63. And more importantly, at the evaluated alert threshold, it missed 67% of patients who developed sepsis, while potentially generating alerts for 18% of hospitalizations. So, think about the human experience behind that number. And by human, I mean like in the sense of healthcare. Healthcare, it would be like the doctors and the nurses, essentially the healthcare providers, right? So a nurse or a physician does not experience does not have any experience in like what area under curve or AUC means, but they just experience a notification, and one notification over after another. So when most alerts do not lead to successful action, in our case like 67% of them were like false or something like that, right? um, you know People tend to adapt, so they start ignoring this model's results. They start they just start clicking through them, they silence them, or mentally kind of filter them out. And this is not, we're not blaming clinicians here. They're not being careless. That's just the system training its users not to trust it. So during the first COVID wave, one institution paused these alerts after reports are, over alerting. So they just bought this entire sepsis model, and then they tried using it, and they just stopped it. The important point here is that the model may not have suddenly changed, but like patient population, workflow, alert volume, operational environment, the all of these could have changed. So what do you think actually failed? It's not just the model. It's actually like the system behind it. In most cases, the actual foundation model, or AI model or machine learning model does not really um, should not really take blame here. It's essentially the system around it. So that brings us to the main argument of this talk. Trust in AI is not a model property. It's a system property. So model performance, though it's not the deciding factor, it's definitely, the performance is definitely necessary. We need to kind of account for all sorts of statistical metrics to assess a model. But like obviously we should not deploy a model that performs badly, whatever the metric might be used to measure. But a good model can still produce a bad system. So it can consume stale or corrupted data. It can be called outside the population of which it was actually validated. It can present an uncertain result as a confident answer. Like this is very common, right? So you give AI or so, you ask AI something. It says, okay, I've done the research, here is the definitive answer, and then you say, no, but I think it's this, and then AI says, oh yeah, you're 100% right. So it confidently can give you an uncertain answer, right? So it can interrupt the operator so often that the important alerts actually become indifferent from noise, right? So or it can hand in, or worse, actually, it can hand an incorrect result to another agent, which treats that result as an established fact. So if you're using like multi-agent architectures, so one agent can produce a wrong result and give that wrong result to the next agent. The next agent thinks that the first agent is correct. Like, it doesn't really care what's right or wrong at this point, right? So there should be some sort of guardrails which we'll discuss in this session. So in traditional machine learning discussions, we often stop at the model model boundary, as in like model statistic or metric, like the area under curve, F1 score, precision, recall, all that fun stuff. But system architects, they have to keep going. They have to go beyond these metrics. We have to look at the data pipeline, the action boundary, the interface, the fallback path, the audit trail, and finally, like, a human handoff. Healthcare is my running example because the consequences are easy to understand, but the architecture or the system is not specific to healthcare. It can and should be used uh, everywhere, in my opinion. So, coming to the problem, right? Like, how does a probabilistic system fail? So traditional software often fails loudly. If something's not right, the service throws an exception, like client side or server side exception, or the availability goes down, or the latency spikes, or health check goes red, or um, dependency timeouts and things like that. It'll fail pretty loudly, and it's very clear. You'll have a stack trace. You can read what's going on. But like an AI system or an AI model, it can just return a 200 or an okay response, and it'll produce like a syntactically valid JSON object and still be completely wrong, right? So that's why ordinary availability monitoring is not enough for AI models these days. We need to come up with new kinds of metrics to evaluate. So the first failure mode is, as you can see, is the distribution drift. What is that? Right. So that's essentially the data. So the data reaching the model begins to differ from the data on which the model was actually developed or calibrated. So, let's say in the case of healthcare itself, like a hospital, changes coding practices, and coding practices is like the disease codes or illness codes. Maybe a lab changes units, maybe patient demographics change. The API would still be healthy, confidence remains high, and usefulness, it quietly declines. The second is reasoning or composition drift. So imagine a summarization agent omits a medical allergy. Um, so let's say you have like 10 different allergies, things you're allergic to, but like an AI agent that's specifically used to summarize um, your health, it misses one allergy, right? That's pretty dangerous. So a recommendation agent then treats that summary as like a patient record, and from then it just starts completely deleting that one allergy that you had, right? So and then in this chain of events, the third agent validates the dosage, but like never sees the missing allergy. So each component looks locally reasonable, if you look at it just specifically for each model, but the composed system it's very unsafe. And thirdly, and finally, the automation bias. So when a system is usually right, humans naturally uh, reduce their scrutiny. So when an AI just starts giving you satisfactory answers, you start to trust it more, and you start to not validate or verify it as much. Right. So the human in the loop may like the human may technically remain in the loop, but it just becomes a rubber stamp at that point. So these are not simply like model quality problems, and these are architecture, like system or human factor problems. So we need controls that operate outside the model's reasoning processes. All right, now moving on to the safety shell itself. So that control layer that we're talking about, that layer is the safety shell itself. So the basic idea is simple, like allow the probabilistic model to propose, but require a deterministic or independently verifiable set of controls before the proposal actually becomes an action. So this is not like one product or one framework. It's like a boundary. So a circuit breaker, for example, like it prevents a failing dependency from taking down a system. An IAM policy limits what a service is allowed and can and cannot do. A database constraint prevents an invalid state, even if the application has a bug. Um, the safety shell applies that same mindset of to AI, essentially. So I divided the behavior into like three explicit failure modes itself. So the first one being the fail safe mode. The system blocks the action and escalates. That's the fail safe. So it's essentially failing loud. You could think of. If the requested action violates a hard clinical rule, and again in terms of healthcare, like it like for example missing an allergy, that's a pretty hard clinical rule. And that there is AI should not be creative in this case. It should stop. That's what failsafe should be. The second being the second is the fail degraded option and a scenario, and here the AI path is unavailable or insufficiently reliable. So it's simpler, safer service remains useful, and the service remains useful, but maybe the system provides a rule based response or produces a draft without actually executing an action. So essentially you will want a human to review the provided output, because the model is not very confident. um, you know the third one is third situation is the fail operational. So here continuity matters enough that the system moves to an independent backup path. So the backup should be meaningfully diverse, like not merely the same model with a slightly different prompt. So here the shell doesn't magically identify every correct answer. What it does is it detects and contains the failure classes we know, and we know how to define. So obviously this is not working code, but just representation here. So what would that shell kind of look like? What would those three modes or failure situations look like? So here is this is an intentionally kind of a boring version, and boring is a good is good in safety. So like before the model output leaves the system, we check a few things. So first, does it violate a hard invariant? Like for medication workflow, that could be a documented allergy or a controlled substance restriction or dosage limit or an unsupported patient category. If yes, of to any of these or all of these, just block the entire flow, stop it there, and alert a human. right? Model confidence is irrelevant here. And second check is essentially the result of sufficiently calibrated, just checking whether the result is calibrated enough for this use case. So, for example, let's say somehow it calculates the confidence as 0.70. In a real system, you would want to have your own threshold, but it's just for illustration. So once you determine your confidence threshold, um, if it does not meet that criteria, uh, that should give specific error codes and call for a clinician review, essentially. The third one is the drift. Fail operational. So is the system detecting a drift or any unfamiliar inputs, right? So if yes, the response might be a rule based fallback, or an escalation to a human. So a current real world example actually is Utah's doctronic prescription renewal pilot. So it operates within a restricted formulary for medications that have already been prescribed, and it excludes categories such as controlled substances and exists inside a time limited regulatory program. So the architecture lesson is not that this particular system has solved autonomous medicine. The lesson is, a narrow lane autonomy, essentially. So the system is allowed to operate inside a bounded action space. That's how we should kind of think about it, with defined exclusions and escalation paths. So the second pattern is, we should surface uncertainty. Related to the previous slides, fail safe, and um, the other two as well. But a screen, that says sepsis risk of 85%, right? It looks scientific and precise, like, but what does that number mean? What is that 85%? Right, so, and how is that calculated, and is the model calibrated? Is the patient similar to the calibration population? Is 85% the probability of sepsis, or is it the confidence of the model itself, or just a random score that we market, right? So we don't exactly know, and a single number often creates more certainty in the interface than exists in the underlying system. So one alternative is conformal prediction. So instead of forcing one answer, the model can return a prediction set. So for example, pneumonia or heart failure, right? So with a target coverage level under the method's assumption. So essentially, like, going one level deeper, like, and like, kind of reasoning why why that number has been, or how that number has been calculated, and what kind of categories matches the closest. So the important human message here is, the system has enough evidence to narrow the possibilities, but not enough to distinguish confidently between these alternatives. So that's a more honest and a more useful result. So uncertainty should also change the system behavior. So for like highly uncertain case, do not just paint the number orange, and route it differently, require additional data, invoke another source, another data source, slow down the workflow or escalate it. So pattern 3 here is a multi-agent quality control. So the one disclaimer here is that this is not deterministic again, because you're relying on another AI model. Although you can set your own set of guardrails and things like that, but yeah, just a call out. So uh, adding agents essentially does not automatically add safety, again because of the same non-deterministic flows. Also, like two LLMs can agree and both can be wrong. They may share the same training biases, retrieve the same incorrect source, or follow the same flawed context. So I think of multi-agent quality control in in layers. So a recommendation agent can generate a proposal. A reviewing agent can check reasoning quality, missing evidence, or inconsistencies. So but hard invariants should still be enforced by deterministic policies or authoritative tools. So, for example, an agent can ask, "Does this recommendation appear inconsistent with the documented allergy?" But the final allergy check should query the structured patient record and apply an explicit rule. So the reviewing agent is valuable because it can find semantic problems that sometimes simple rules miss. Like there can be many edge cases, and sometimes AI can catch these. The deterministic policy layer is valuable because it does not reinterpret the rule, essentially. So, together, they reduce the chance that one component's mistake silently becomes another component's ground truth. This also gives us useful operational signals. Or if one agent is consistently being rejected, that is not just a failed request. It tells us exactly where the system is weak. The pattern 4 is the auditability layer. Did I say that right? Auditability, yes. Auditability layer. So when an incident occurs, you know, the model made a bad call. If AI just says the model made a bad call, that's not the root cause. That's what happened, but that's not the root cause, right? So we need to know which model version ran. We need to know which prompt or policy version was used, what data was retrieved, what data was used, which tools were called, which agent produced each intermediate output. If in a multi-agent architecture, what constraints were passed, and whether a human altered anything in the process. So the log should be, all of this should be logged so that it can be audited, and these logs should essentially be append only. No modifications or deletions, essentially immutable, right? So it should be access controlled, it should be tamper evident, essentially append only, and detailed enough to reconstruct the relevant state. As I think the father of AI itself said once, we don't know, nobody knows how an AI is producing that output. It's like a black box, so you just give it something and it just produces something. We don't know what's going on inside internally, which is scary, right? So we need to make it in a way that we need to at least log it in a way that it is auditable, and we know what we at least get the best picture of what happened, why it happened. That that doesn't really mean logging every raw token and every piece of protected health information, which can easily lead to legality issues. And none of this information should be stored forever as well. So in a regulated environment, observability and privacy have to be designed together. Essentially, that's the point I was trying to kind of convey. We should use things like data minimization, tokenization, encryption of sensitive fields, and etc. Things like that. So we should also define like retention periods, restrict access using IAM, and hashes where full payloads are unnecessary. In most cases, full payloads are unnecessary. So essentially, auditability supports incident response, compliance, evaluation, and account. Mainly, I guess, most importantly, accountability. So it also makes improvement possible. So we can always feed this into like another model, or when we're training the model for like drift. Um, Without any of this trace of what happened, every failure becomes an anecdote, essentially. So finally, the pattern five. I know that's essentially a phased autonomy. So teams often talk about autonomy as a product capability, but either the system is autonomous or it's not. But I think that's the wrong abstraction. Autonomy should be an operational state that the system earns for a specific task, task population and risk category. Start in shadow mode. The AI runs, but it cannot affect the outcome. Compare its behavior with human decisions and collect failure cases. Essentially, you are running the model, but and it's giving you the output. The human still makes every single decision, and the human just checks whether what the AI did, how the AI did. Did it output the right result or not? And collect these failure cases, note it down, and then we move on to the assist mode. Now here the system produces recommendations, but every recommendation is reviewed. Um, Next is an oversee mode. So this system acts only within low risk, well characterized cases. Humans again review exceptions and statistically meaningful sample of ordinary cases. And finally, we have to go into the monitoring mode. So here the system has more operational freedom, but not unlimited freedom. Drift, calibration, safety violations, and human overrides are monitored continuously here. So the rollback condition should be defined before the promotion. Um, so, for example, if calibration error exceeds a threshold, if a critical invariant is violated, if override rate changes sharply, or even if the input population shifts beyond the validated range, the system automatically returns to a lower autonomy level. So it has to go, from let's say it's at monitoring, and then it's at the monitoring level, and it's like, okay, something's wrong, it should come down to oversee, and then something's still wrong, it should come down to assist. It should kind of restrict its own capabilities. Um, so essentially, I guess the best way to kind of put it is, it has to be it has to have a reliable elevator back down. I think that's a good way to kind of put it. All right. So once we change the architecture, we also need to change the dashboard, the metrics that we measure. We should, I would not remove things like accuracy, sensitivity, or specificity. They all remain essentially essential, but they're not enough to describe whether a production system itself overall is reliable or not. Um, you know, so we have to add calibration. So when the system says 40% risk, does the event actually occur approximately 40% of the time in comparable cases? Need to be sure about that. We should add net benefits. Does using the system create a better clinical outcome than existing practice once the cost of false positives and false negatives are included? Another thing we can add is drift metrics. So here you have to check, are the inputs, predictions, errors, or patient populations changing. So the other one, I think the one that I actually like a lot is the override and acceptance behavior metric. So essentially, this would be like an override rate. And why I like it, it's because um, it measures what the clinicians actually do, or the operators actually do, not just what they say. So essentially, like as you can see here, like if in a really opaque system, it's 74% override rate. That means 74% of the time the model was wrong or ignored, and the clinician just overrode it, saying, I can make a better decision or I made a better decision, right? But once we implement all these systems, it can go down to 15%. So 15% override rate is great, right? Um, so essentially, we should aim for the lowest possible override rate, and you know a very low override rate can indicate appropriate trust, essentially. So override rate, I think I associate that with like trust metric. Yeah. So when you pair it with like downstream correctness, patient outcomes, and calibration and audit results, it becomes a pretty powerful um, system. And just to be clear, the objective is not like maximum trust. It's just appropriate reliance. So trust in the system when it's um, competent. Question it when the evidence is weak, and reject it completely when it crosses a specific boundary that you set. So this is a practical maturity model I use to kind of organize the ideas. It's not an official industry standard. It's just a way to kind of ask where a system is today and what the next meaningful improvement should be. So here at level one, the raw model output reaches the user or another service with almost no mediation. I think we were at that point maybe 2 years ago, but we've then evolved. At level two, the teams had basic thresholds, formatting checks and content filters and all this kind of stuff. And most of the agentic workflows are at this stage today. At level three, the system becomes socio-technical. It has defined failure modes, deterministic policy boundaries, human escalations, and explicit ownership. And I think this is where it should be. It's kind of like the sweet spot, and that's where the talk today is coming from. And level four and five are crazy levels. So level four are basically decisions become reconstructable, and uncertainty is evaluated systematically. The system can demonstrate why it permitted, rejected, or escalated an action. And level five is essentially monitoring, rollback, deeply automated, and human feedback hardly exists here. Um, Level five, though it sounds good, attractive, it should not be the first objective. For most teams or most use cases, the highest value would be going to level three. Um, Yeah, so healthcare makes the stakes vivid. It's easy to kind of explain, but the engineering behind this is kind of generic. In finance, a model may recommend an action based on a malformed feed. A deterministic exposure limit should still block the transaction. In industrial control, an agent may misread a sensor or infer the wrong operating scale. Physical constraints should cap what it's allowed to command, and so on and so forth. Essentially, probabilistic proposal, deterministic boundary, explicit uncertainty, um, controlled action, and finally, we should aim for the auditable result. So essentially, I want to leave you with five patterns. You know, Safety shell, where you build a probabilistic component and define what happens when a check fails. The second being the surface uncertainty, essentially honesty, and let uncertainty change the workflow. Third, using multi-agent review where it adds value but enforce hard invariants outside the agents. The fourth one being make the decision chain reconstructable, and finally the fifth one being let systems earn autonomy gradually with rollback designed from the beginning. Yeah, essentially the goal is not to create an AI model that that replaces the expert. It is to build a system that an expert would trust with a real decision and would know when not to trust. And thank you, and happy to take any questions.
Okay. Okay. Thank you very much, Sanjay. Do you think? Yeah, I would say thank you for this presentation. It was very interesting and gave us a kind of practical, how I can say, perspective on how to make AI agents more reliable and in a high environment. We
Yeah.
received several questions from the audience, and unfortunately, because of the time available, we had to select only a few of them. And for additional question or further information, please feel free to contact Sujay directly on LinkedIn or other social media. So let us start with the first question. The first one is sent by Mark. The question is, what inspired you to create the safety shell concepts?
No, thank you for the question. Yeah. So essentially, what inspired me was the gap between how we evaluate AI and how AI actually fails in production. So we usually focus on the model itself, the accuracy, the AUC, the F1 score, just all these performance metrics, right? So, but when you study like real world failures, especially in a place like healthcare, right? The problem is of often somewhere else. The input data changed, or the model was used was not right for this specific use case. And how do we know all of these things, right? So the epic sepsis case is a strong example of why we should have this safety shell concept. Yeah.
Thank you. So let's move to the second one. How does the safety officer agent prevent one bad output from affecting the entire agent pipeline?
So the safety officer is actually very. It totally depends on your specific use case and how you kind of add rules to it. So a safety officer essentially acts as like an independent checkpoint between the agent producing a recommendation and the next stage of the workflow. It's like a
Mhm.
middleman. It kind of makes sure that the next model, again, you can model it in different ways, but like you can make sure that the next agent is um, getting the right facts and not wrong um, input from the previous agent. So for example, imagine a recommendation agent that proposes a medication, and the safety
Yeah.
officer could verify whether the recommendation conflicts with the patient's allergies or allergy history, whether the medication is permitted for that workflow, um, and whether the recommendation is supported by the retrieved clinical guidance. So it definitely helps. So but it totally depends on how you kind of configure it, and it's an open kind of canvas. It totally depends on how you want to use it.
It depends on the context. Okay, so thank you. Let us move to the next question. What is the most common failure you have seen with AI agent in productions?
Um, So the most common failure pattern I've seen in production AI systems, and repeatedly in the case studies actually behind the stock, is silent failure at system
Okay.
boundaries. The model does not crash.
Mm.
It still responds with a successful response.
Yeah.
The output is properly formatted, and but something important is really wrong behind the scenes. I think that's one pretty big, essentially data staleness and wrong. AI hallucinations also is a big thing, big issue.
Sure. And the next question is, how can a company start implementing a safety shell with a small AI project?
So I would start much smaller than most teams expect. So it's always the case where you think you need the highest level of security, but you don't. So let's not don't over engineer it. And first identify exactly what the AI is allowed to do, or essentially what you want the AI, what you allow the AI to do. Is it just drafting text, or is it making a recommendation that can affect you financially or medically or physically or whatever it is, legally? Is it just calling an API, calling specific tools for a like very small set of results? Modify it. Does it have to modify data? Does it, or is it literally taking any action on your behalf? Right. So once you identify this, the picture kind of becomes a little more clear. And secondly, write down the conditions that must never be violated. This can be like a living document, or it keeps changing, and you can definitely keep changing the rules. So once you write these conditions, it becomes very clear on that these are your hard invariants, so these should be your main fail safe. For like a customer support agent, that might mean it cannot issue refunds above a certain amount, right? So something like that.
Okay, sure. Yeah, sure. Thank you. And the final question is, what advice will you give to teams deploying AI agent in kind of high environment?
Yeah, so for this, I guess my main advice would be to architect for failure instead of assuming you can eliminate it. So I guess here is like you have to be a little more, or you have to make the AI be a little more cautious about things. Like it's okay to kind of, I would say it's okay to kind of overthink here, and like and fall back on more conditions than usually required.
Mm-hmm.
I'll focus on like keeping your action space narrow. Hard invariant should be outside the model. Make uncertainty operational, and essentially don't aim for level 5 of autonomy and things like that.
Okay, thank you. We are close to the hand. Unfortunately, we cannot take all the questions, but before we close the session, Sujay, would you like to share a few final words with our audience, perhaps one key message or recommendation that you would like them to remember from today's session?
Oh, I don't think I fully heard you, but are you asking if I would just like to say a few final words?
Yeah,
Oh, yeah, yeah.
and
So no,
some advices for our audience.
so some what? Sorry.
Some recommendation you would like them to remember from the today's
Yeah,
session.
yeah, absolutely. So I think what I want, or what I would love people to take away or remember from this is, like trust in AI is not a model property. It's a system property. So let's design the
Yeah,
system, not
sure.
the model. There are people already, there are smart guys design, making smart people, creating all these models, AI models and things like that, that half of them even they also don't understand. So let's kind of make build reliable systems around these models. I think that's a key takeaway.
Okay, great. So thank you, Sajay, for this final word, for this excellent session. Thank you also to everyone who joining us today. We hope you found the session useful and inspiring. We look forward to seeing you again next Friday for another Archive Friday session with a new speaker and a new topic. Have a good day and see you next Friday. Thank you, Sanjay.
Thank you so much for having me. Thank you. Thank you, everyone.
Thank you.